Welcome to this introductory offering of our course, The Mathematics of Waves. This is the second lecture of week 2. Now, in the last lecture, we introduced this idea. I guess we introduced two ideas. One is that if you take a basic oscillator unit and string together n of them, you get a wave system, which will show wave-like behavior. And the second concept that we introduced towards the end is that such a system behaves as if you have n independent oscillators, each with its own separate resonant frequency. Okay? And that's a very powerful concept because when they're coupled together, you can simulate it on a computer, but when you want to think about it, that makes it complicated because it's all coupled. Whereas if you have independent oscillators, that's much easier to think. Right? And that's this concept of normal modes, which we'll talk more about in this lecture. Yeah. Now, if you look at the equations that we had, if you remember, we wrote them down from the circuit equations. And if you have, say, a unit with 5 oscillators strung together, then you have 5 currents, 5 voltages, and after scaling them properly, you have a set of equations, set of 10 equations, and this block is 0, that block is 0, whereas here you have a block which is minus omega times this matrix, here it's plus omega times a similar looking matrix, but a little different in the sense the diagonal elements are the same, but one has a lower diagonal while the other has an upper diagonal. When we're dealing with oscillators, you remember we had a differential equation looking like dx dt equals ax plus s, and x had 2 components, and when we diagonalized it, we got 2 eigenvalues, and they were conjugates, complex conjugates of each other. Now, we could do the same thing with our present set of equations, but now, of course, it's not 2 by 2, but rather it's 2n by 2n, you see? And so you'd actually get 2n eigenvalues, 10 in this case, see? And there would be complex conjugates, so it would be kind of equivalent to 5 separate oscillators. So that's the basic idea of the normal mode, that you start from the exact set of equations, but then if you diagonalize it, you can break it up into independent oscillators. And numerically, you could do that using one of these tools on MATLAB or Python. Just diagonalize it, find the eigenvalues. Previously, we had a 2 by 2 matrix, which gave us 2 eigenvalues. Now we'll get 10 eigenvalues. That's it. So that would be the numerical approach. But what we want to talk about, though, is a more conceptual approach, something that allows us to do things on paper, you see, without going to a computer, and gives us a framework for trying to understand what it is the computer is telling us. In order to get these simple analytical results, one of the assumptions that's very useful, there are other things one could do, but this is one that's relatively simple and we'll use this, is assume that your set of n oscillators is terminated in what's called a periodic boundary condition. In other words, as if they form a ring, meaning you have 1, 2, 3, 4, 5, and then you take the output from 5 and put it back into number 1. So it's like a racetrack going round and round and round. See? And if we assume that, then as you'll see, you get some very relatively simple results that provide us a nice framework for understanding actual simulations. First thing we have to do is, when you put in this periodic boundary condition, this ring, you'd have to modify these matrices a little bit. Because you see, what happens is, if you look at this first line, when you're talking of di1 dt, so you have this term here, which multiplies V1. Now, what we'd have liked to have written is V1 minus V0, right? But then V0 is not in our list of variables. It goes 1, 2, 3, 4, 5. There's no V0. But because of the periodic boundary condition, you see V0 is the same as V5. And so this V1 minus V0 becomes like V1 minus V5. And so I can put a minus 1 at the other end. Same with this dv dt, that when you looked at the dv5 dt at this end, you want to look at the difference between the current I5 coming in and the I6 going out. But there is no I6 because variables end from 1 to 5. There's no I6. But then because of the periodic boundary condition, the I6 is the same as I1. And so you can put in the minus 1 over there. So that's the modification. These two elements get changed a little bit. But with this change, actually, we get a matrix whose eigenvalue, which can be easily diagonalized. And that's why we are using this boundary condition. Although I can imagine there could be some systems where you actually have a periodic boundary condition, where you're actually making it into a resonator, not by putting an open circuit and short circuit, but actually by taking one output and tying it back to the input. Okay. Now, with this modification then, after that, I could write my set of equations, this set of 10 equations, 10 or 2n equations, in a more compact form, something like this. So you have these two blocks are zeros. So actually, this is also a matrix 0, and this is a matrix 0. And on the off diagonal, these blocks, you have minus omega times what I will call the B matrix. And that's exactly what this is. 1 on the diagonal, minus 1 on the lower diagonal, and then this extra minus 1 coming from the periodic boundary condition. And you'll notice what I have in this block is exactly the transpose of that one. So I have plus omega times the B transpose. So this then is a compact way of writing these equations, where note that these i's and v's, each one is like a n by 1 column vector. This B is like a n by n matrix. And what I've written here as 0 is really a n by n 0 matrix. Okay. Now the thing is that this matrix B, it's very easy to write down its eigenvectors. Because what you can convince yourself, what's an eigenvector? The idea is you want a vector such that when you multiply it with B, you get some number times the same vector. And what you can show is that if you define a vector like this, e to the power minus jka, j2ka, etc., all the way to e to the power minus jnka, and k can be anything. But if you write it this way, then B acting on this will give you exactly the same vector, but with this factor in front, 1 minus e to the power plus jka. The 1 comes from this 1 on the diagonal, and then there is the minus 1 comes from this lower diagonal part. And you can convince yourself that indeed B acting on this will give you that. Now, if you take B transpose acting on this, you'll get a similar result. This is also an eigenvector of B transpose. But instead of 1 minus e to the power plus jka, you have 1 minus e to the power minus jka. So these are basically the eigenvectors of B and B transpose, which means, you see, the nice thing is I'm able to write this down without doing any numerics. I didn't have to go to MATLAB or Python for this. I can just write it down analytically, without doing any numerical calculations. And for any k, this would be true. And then what that means is I can diagonalize this essentially without going to a computer. So what would happen then is if I diagonalize it, then this matrix, which was not diagonal, will now become a diagonal matrix whose diagonal elements look like this. So each k labels one of the elements on the diagonal. So there'll be omega 1, omega 2, omega 3, all the way from 1 to n. And same here. Here it is 1 minus e to the power jka. Here it's 1 minus e to the power minus jka. And this minus and plus, that's what we had before. So finally, using this idea that it's easy to write down the eigenvectors of B and B transpose, I can essentially diagonalize it. So now, so you could view this as a kind of a basis transformation. You see, back in week 1, when we were doing oscillators, if you remember, we did some basis transformation in this lecture 1.5. See, where we're 2 by 2 matrix and we did the transformation, diagonalized it. Here also we have this same basis transformation T inverse, but now it's a much bigger thing. We are diagonalizing a n by n matrix, capital N, which could be 10, 100, even 200. See, but the nice thing is, because of the structure of this matrix, you can actually diagonalize it directly. And these matrices, these transformation matrices, have this form. Right? That corresponds to what we did before. Now, what you might wonder then is, how would I get these transformed variables? Well, exactly what we had before. If you want their transformed currents, take T inverse times your the original currents. The currents in the nth section, but if you transform it, you'll have the K component of the current. Similarly, the voltages. And as for the matrices, you have the similarity transformation. So if you take B, put a T inverse in front and a T afterwards, T inverse B times T will give you a diagonal matrix whose diagonal elements will look like this. Similarly, B transpose, do T inverse B transpose T, you'll get a diagonal matrix. So that's this overall similarity transformation. Now, what you might wonder though is that when I wrote this down, I said that, K can be anything. Okay, but here I'm implying that K only has capital N values. Because if K can be anything, then when I do this transformation, if I started with a 10 by 10 matrix, after transforming, it won't be 10 by 10 necessarily, right? If K had 100 values, then you see I'd have 100, become a 100 by 100 matrix, and that doesn't make sense. I mean, this similarity transformation takes a 10 by 10 and makes it into a 10 by 10. Now, and that is why you have to bring in this extra condition which limits the value of K to 10 values. If you have, say, 10 sections. If you have 5 sections, it will limit it to 5 values. And why is that? Well, that's because there is this periodic boundary condition, which says then that every time the voltage or the current on the small nth section is e to the power j n k a. But because it's periodic, if I add capital N to this, I should get the same number again, because they both represent the voltage on the small nth section. Okay? Because adding capital N shouldn't make a difference because it's a ring. You see? So what that requires is that e to the power j capital N k a should be equal to 1. And that requires that ka be equal to 2 pi over n times an integer. Nka is some multiple of 2 pi. And the allowed values of this integer, well, there's n of them, 0 to n minus 1. Because if you put this integer equal to capital N, that's equivalent to putting it equal to 0. That's just everything's modulo 2 pi. Okay? So that's it. This is the condition then, coming from this periodic boundary condition, that limits your allowed values of K to capital N. So you originally had capital N voltages and capital N currents. After transformation, you still have capital N of them, but then now they are labeled according to the values of K. And Of course, the nice thing now is that these are all diagonal matrices, and so the kth oscillator is completely independent. So if you take k values go from this 0 to capital N minus 1, and each one is an independent oscillator, and I can solve a little 2x2 equation for it. And the 2x2 equation this is on the 1, 2 element, and this is the 2, 1 element. And each k then here will give you two eigenvalues. These are complex numbers, but it will give you an eigenvalue which will depend on the magnitude of that. You can show that the eigenvalues of this will be plus j times the magnitude of omega k and minus j times the magnitude of omega k. And what's the magnitude of omega k? Well, this is a complex quantity, but if you do a little algebra and find its magnitude, so in other words, you write out the real part and the imaginary part, square them, add them up, and take the square root, you'll get this quantity. So the magnitude is 2 omega sine Ka over 2. And then there's a phase to it. But that's this element with some phase here. Okay. Now, if you plot this out then, so you have all these different values of k, each one corresponding to an independent oscillator, and corresponding to it we have the oscillation frequency, omega k. And that omega k is given by 2 omega sine Ka over 2. And that's what I've plotted here. Okay. Now, so that kind of puts on a quantitative basis what we had said before, that when you have a string of n oscillators like this, you have a wave system, but you can think of it as n independent oscillators, each labeled by a different values of k. Of course, this condition was obtained using a specific boundary condition, and depending on the boundary condition you use, the details of that condition could change somewhat. But the basic spectrum would look much the same, especially when n is large. So you have lots of frequencies close by, and each one is somewhat broadened. Then the details of exactly where the resonances are doesn't matter as much. Okay. So now let's try to think of a problem where you have a sinusoidal excitation, let's say. So in other words, we have a string of oscillators that form a wave system. It is terminated in these resistors, and from this middle I put a cosine omega t excitation right in the middle at delta in x equals 0, which we assume is in the middle. And I'd like to know how much power is delivered. Well, this is where the independent oscillator idea is very useful, in the sense that what we did last week was we said when there's a single oscillator, the power delivered is so much. There's this delta function, and the power that is drawn from a current source is so much. Well, now we have a whole bunch of oscillators. So what I have to do is write the power delivered to each oscillator and add up all the oscillators. That's it. That's the power of this normal mode approach, that you can treat each one individually, independently, and go from what we learned in week 1 about single oscillators and apply it to a wave system like this. Now, let's show how you can evaluate this to get a sensible answer. So that involves a few steps. So the first step is the summation over k. When you have many sections, so it's a long system, that means capital N is large. Remember, this number of peaks depends on the n. So when you have, say, 9 of them, we had 9 peaks. But if you have 100 of them, there'll be hundreds of peaks. And in general, for a long system, there are lots of them very close together, and each one will be broadened enough so you'll get a kind of broad response like this. So in order to evaluate that, what you do is you replace the summation over k with an integral over dk. And the point is, so how many k values are there in a given range dk? We'll note that The allowed values are spaced by 2 pi over NA. Why? Well, remember, Ka is 2 pi over n times an integer. So the allowed values of K are spaced by 2 pi over NA. So in a given range dk, the number of oscillators I have is dk divided by 2 pi over NA. So that's the first step. Replace this summation. Next question is, what's this ik square? So what is the source term that is driving the kth oscillator? Well, I know the actual source term in terms of this capital I. It is non-zero in the middle section and zero everywhere. But what is the source term ik? Well, you have to do this transformation, T inverse Kn times that. And notice that T inverse has a magnitude of 1 over square root of n. So when you multiply this out, it's easy because everything's zero. So you get Is over square root of n. And the phase factor doesn't matter when you take the magnitude square. So it's Is over root n square. That's it. And then finally, what about the resonance frequency of these oscillators? And there, you get a relatively simple result, you see, if you assume that your excitation frequency lies in the lower half of this thing, down here, where things are kind of linear. So in this region, you see, what you can do is you can replace the sine x with x. So what you then get is omega times the magnitude of Ka. So that works down here. And if you do that, then you see, instead of omega k, I could put omega Ka. And now I can evaluate this sum in this limit. I just collect all the constants together. These constants, I string them together. And then I'm left with an integral dk over a delta function. See? And the delta function is omega k minus omega, and omega k is this omega ak minus omega. And this integral, when you do it, this delta function, when you integrate it, you get 1 over omega a. And I have to multiply it by 2 because I guess I'd get one peak in this delta function when k is positive and one peak when k is negative. So we end up with a factor of 2 there. So that's it. And when you put that together, you'll notice these things cancel out and you get Is over 2 squared times Z0. So we went through a bit of algebra and it'll take you a little while to get comfortable with it. But at the end, you get a pretty simple result. But this is a result actually you could have kind of seen without going through all this, without going through the idea of normal modes and all that. The way you could have seen it is something like this. You could have said, well, this Is cosine omega t, kind of half of it goes this way, half of it goes that way. So what goes this way is dissipated in this terminating resistor. So you take that Is square Z0 and equal amount is dissipated on the other side. So, and then there's a cosine omega t. So when you square it and time average it, you get a factor of half. But then there's 2 of them. So the half and the 2 cancel. So finally you get Is over 2 squared Z0. So you could have kind of seen this answer from more elementary arguments. But I really wanted to introduce this way of summing over independent normal modes, independent oscillators, because that's a very powerful method, you see. And actually, I'll use this more in the last lecture again, when we will be doing a much more difficult problem involving waves in 3 dimensions. This is just a one-dimensional thing where it's relatively easy to see to get this answer. But this method of normal modes is much more general and works even when you have complicated boundary conditions and the modes themselves are not as simple. It'll take you a little more work to evaluate the modes, but then you can again use this idea of normal modes, which is a very nice property of linear systems, which you have here. Because if it were nonlinear, then you cannot superpose solutions etc. It works for linear systems, and it's a very powerful conceptual tool. Now, notice though that we made an assumption that we were in the lower part of this curve. This is often called a dispersion curve, you see, which shows the frequencies of the oscillators as a function of this k value that labels it. See? And you're kind of in the lower part of the dispersion curve. And that is where it behaves more like a normal wave with a well-defined velocity. See? Because if you may recall from some early physics courses that, waves have this, what we call the group velocity, which is actually the slope of this curve. And down here, because it's linear, there's a nice fixed velocity. So when you use a frequency down here, what is relevant is this region of the curve, and there you have a nice well-defined group velocity, and you see this behavior that I showed you earlier. If you plot the things, you'd see these peaks and troughs, which are all propagating with a constant velocity. But if you used a frequency that was kind of closer to the top, somewhere around here, right below this 2 omega, then you notice right around here, things are not linear at all. And the propagation is much more complicated. It isn't like a simple wave that is propagating with a single velocity. And previously, if you had looked at a particular section, you'd have seen a period of time that it takes for the wave to arrive there. And after that, you see a nice sinusoidal oscillation. But with this frequency, you won't see anything that clean. You kind of see this thing building up because waves have different group velocities. Each one is appearing at different times, and it has a more complicated response. And if you actually increase the frequency further, so you are outside this band, then you'll find the wave can't even propagate. You see, you excited it here, it just stays right around there. And if you look out here, you just see some little small wiggles. That doesn't even propagate because there are no oscillators to respond at those frequencies. So this picture that wave system is like a bunch of independent oscillators. And when you excite it with a certain frequency, what you do is you pick out the oscillators of interest right around that frequency. See? And if you are down here, then you have nice wave-like behavior with a well-defined velocity, which is given by the group velocity. But once you get close to the top, it's not so clean anymore. And if you are over the top, it doesn't even propagate. Now, how real is this? Do you really have this cutoff frequency? And the answer is yes. If you had a ladder circuit like what we considered, the one with these L's and C's, each having a length of this section of length A, then indeed there is a upper cutoff frequency determined by square root of 1 over LC. So another physical example of that, which we won't go into in this introductory offering, but in the full course eventually we might cover some of that too, is that people often think of a solid lattice. A solid has all these atoms that are arranged in a lattice, and people often visualize it as a mass and spring system, as if each atom is like a mass, and which is connected by a spring to the next atom. And there's a equilibrium distance when the spring exerts no force, but if you try to squish it or pull it apart, then the spring exerts a force. So you can build up a mass and spring system. And remember, back in week 1, I think lecture 1.3, we said that LC circuits were kind of like mass spring systems. And so just as you can build up a wave system by stringing together these LC sections, you could build a mechanical wave system by having these masses and springs in a lattice like this. See? And in that case, you see this A is a real thing. It is basically the atomic spacing. And with solids, often, these mass and spring, if we went into the details of what these are, you'd find the sound velocity would be about, sound velocity is the square root of k over m, which would be determined by square root of k over m, as you may recall from 1.3, will be about a few kilometers per second. In solids, that would be a typical sound velocity. And the omega then would be like this velocity divided by a, which would be on the order of terahertz. So indeed, in solids, there would be an upper frequency that would be on the order of terahertz, beyond which you wouldn't have sound waves in the solid. So there are systems where there is a natural section A, section length A, see, and with a natural upper cutoff frequency omega. But there's also other systems we'll be talking about next, where it's actually a continuous thing. Something like, say, a coaxial cable. There's an inner conductor and an outer conductor. And you could view it again like a ladder circuit, but it's just that this A tends to zero. So in other words, the representation with an LC circuit becomes exact when A becomes zero. So, but then, of course, as you make A smaller, the inductance and capacitance of each section also becomes small. But the inductance per unit length and the capacitance per unit length, those stay fixed, you see. And in that case, what is physically important is not so much this omega as the velocity, which is omega times A, because that then is square root of this 1 over the inductance per unit length times 1 over capacitance per unit length. See? And this upper limit that we were talking about, that kind of becomes infinite. In other words, outside the range of interest, because you could view that as velocity divided by A, and as A gets small, it becomes very large, so as to become irrelevant to the discussion. And then you are kind of always down in this regime where you have nice, well-defined velocities. So in the next lecture then, next two lectures actually, we'll go on to examples where instead of this discrete circuit that we talked about, this ladder type circuit, we'll talk about more continuous systems. Thank you.